This class is related about the problems of still calculations. I will not explain the theory of this class because we already did that during the classes. I spoke about the formulas of Euler and the type of failures that we can have, different type of still connections. And we have another presentation that explain, we have another PowerPoint where I explain theory related with columns. I will instead concentrate in the problems, and we will be doing only one problem today. It's the same type of problems that we will be evaluated during module 11. One of the things that is important to understand is that the relationship that a column has between the end condition. What that means, we can have a column with specific characteristics, have a thickness, have a length made with a specific material that is not important in this kind of calculations. But the fact that that column is attached or not, and how it's attached to the top of the structure or to the bottom of the structure will change completely the properties of the column. That makes a little bit of sense. If you have a column that is completely free, you will be able, imagine that you have a piece of wood that you put in the top of a table. It will be easier for you to move this element and rotate it, or move left and right. But if this piece of wood is attached to the desk, for example, it will be more difficult. And if it is attached at the top, even more difficult, it will be more resistant to any load that you will apply. Therefore, it's important to understand the end conditions of the columns. Here we have this graph that you will receive, the same graph in the test, and we will give you a particular end condition. For example, we will tell that the column is completely free for translation, I mean movement left and right if we are thinking something flat, and rotation, I mean having a moment that allows the column to rotate in the top and bottom. If that is the case, you will look in the table where you have the figure of a rotation fixed and translation fixed element. And in this particular case, happens in the sample A. The representation is the column with a line, and an element like this that means like earth, like is fixed in the earth. And that is the case of A. The second possibility is that you have a column that is rotation free and translation free, fixed. What that means, the column is attached, and normally what happens is, this is the same to write pine, is pine to an element that usually is a rectangle with a circle. This column cannot move to the left or to the right, but is able to rotate. And if the column rotates, could start doing things like this. It will move like something like that. You see? That is the type of columns number 2. Number 3, end condition, sorry, the type of end condition. Number 3 is a column that is rotation fixed and translation free. I mean, the column cannot rotate. The column has here an element that do not allow it to rotate. But the column could move to the left or to the right. And that is the case of F, the top of the F. Finally, we have the type of columns that are rotation free and translation free. I mean, the column is completely free. It can not only rotate, but can also translate. And that is the case of E. Well, your column will have an end condition in the bottom and an end condition in the top, and you will choose which of the cases you had. In the bottom, as you can look, the column can be only a rotation fixed and translation fixed, or it could have a rotation free and translation free, like in these two cases. There is not so much degree freedoms in the column, because if not, the column will be in the air. The column cannot be completely free in the bottom, because it will be an object that is not a column anymore. It's not supporting any weight because there is no base. But in the top, the column have the 4 degrees of freedom, 1, 2, 3, or 4. And obviously you can have a combination of them. When you understand what is the end condition of the column that you will calculate, you need to choose a constant that will be the formula. You will never choose the theoretical value. You will choose the recommended design value. For example, if my column is rotation fixed and translation fixed, when I use the formula, the constant K will be equal to 0.865. If my column is, for example, a rotation fixed and translation fixed in the bottom, is the case of this one. I'm sorry. Let me clean this again. I told rotation fixed and translation fixed in the bottom. That means we have 4 possibilities, 1, 2, 3, and 4. And in the top is, for example, rotation free and translation free. We have only 1 possibility, that is this one here. Then the value that we'll use is 210. As you can look, 210 is much bigger than 0.65. And is more than twice the 0.80. These 2 columns, A and B, have an end condition that is stronger. All of them are fixed in the bottom, but in the superior part of A is completely fixed and the other can rotate, and E is completely free rotate and translation. Well, the constant is bigger because the column have more degrees of freedom in the superior and inferior part. Well, I hope this is clear. I will go directly to example number 1. And in example number 1, let me try again here. I already explained all this information before. In example number 1, we have a column that is W 12 by 53. What that means, W is the denomination of a column that is like an I-beam. Usually this is W. I-beam usually is a little bit taller. It's like that. Okay. Well, we have this particular W beam. Many people, by the way, use the word W for any kind of beams that look like an eye. It's called 12 by 53. That means the beam has a height. Let me draw it here. Has a height of 12 inches. And 53 is the weight. The weight of what? We imagine that this column is cut and we have a piece of 1 foot. 1 foot, sorry, 1. And we have the weight of that material. And in this case is 53 pounds. If the column is thicker, this number will become bigger, for example, 100 pounds. That means that the member is stronger. Something very interesting is that you buy steel according with the weight. If you buy a steel that is 50, you buy a column or a beam that is W 12 by 50, every foot will have a specific value, but instead, if you buy 12 by 100, it may cost twice the price. Well, the weight of the steel is important. The heavier, the most expensive will be, the heavier, the biggest base you will have. Therefore, we try always to use the steel that is the less expensive. Well, we have a W12 by 53. A36 is the type of steel because can be A50 or A36. Tables will change. A36 is the normal steel. A50 is a steel that is used only for skyscrapers and tall buildings and bridges. It's a column. It has an embrace length of 16. This is important because if we have a column and this column is attached to a base and is attached to a bracing, for example, a beam, and is attached to something else here. When you do the calculations, we need to imagine that the column is divided in parts. Well, I will calculate this part separate of the other one because there is an attachment there. The column is like divided in several elements. Well, we don't care how tall the column is. We care about the umbrace length, that is the one that we are calculating, that this case is 16. The top is fine, but prevented for lateral movement. What that means? The same that we looked before, different words, but pine means this element here. I mean, can a pine allow you to rotate, but it's prevented from lateral movement. It means cannot translate. That is the type of column. We have an area of the column, we have the radius of the column, and that is all. Well, we need to calculate the maximum load that this column can support. And to do that, we need to use the formula of Euler, and you will receive the formula of Euler in your test. And it will be as follows, something like this. And we will apply the formula of Euler. But before applying the formula, we need to know one of the elements of the column, of the formula, that is K, this element here. Okay, and well, in order to do that, we need to look at the characteristic of these columns. And this column was a column that is fine but prevented for lateral movement in the top, and in the bottom, as common, is totally fixed. Well, we go here, we look which one of the columns are totally fixed, for example, and we will find that the column, let me draw here, the column type A, the column type B, the column type C, and D, all of them here are fixed. And after they told us that the superior part is a pine, is a different word, but that means rotation free, because this is the pine there, and translation fixed. I mean, is prevented for lateral movement. Well, obviously, that is the case of this particular column. It's the only one that is fixed in the superior part and can translate in the superior part. In the inferior part, sorry, can translate in the superior part. Well, you can look that column D also is similar, but the bottom is also translation fixed and rotation free. And no, our column was like this one, completely fixed. Well, our factor will not be 0.7, this is the real one. We'll use the recommended one, that's 0.8. It's a little bit exaggerated. That is the one that we'll be using. Well, now it's very easy to do the formulas and apply the formulas because everything is just simple. We just need to plug the formula into plot the numbers into formula, but we need to be careful about some details. Okay, well, first, we understood that we have all the data, we have the section, we have the radius, we have the length of the column. We even have the type of steel that we don't need it, but 836 can be needed for several things that we'll do later on. And we know that the constant K is 0.8. Well, we have first two steps to do this problem. The first step is to calculate the slenderness, how slender the column is. And the formula is very simple. It's K multiplied by L divided by the radius. K is the constant of slenderness that we already calculated, that is 0.8. I mean, we got from the table. 16 is the length of the column, and 2.48 is the radius that you will receive it. Later on, maybe sometimes you will need to look at the radius in a table, but in this case, it's already there. By the way, there are two radius. A radius that is, in an I-beam, for example, you will have a radius that is going with the sense of the beam in the longer section, and in radius that will be the contrary, is Rx and Ry. we will always have the radius, and that will not be confused because we will use the radius that is the one that made the being bigger, I mean the worst case. Well, in this case, we substitute the elements, but we need to remember that the radius is in inches and the length is in feet. We need to multiply by 12 to put everything on feet. Well, what will be the slenderness? It will be 0.8, that we already got it from the table before. 16, that is the height, divide by 2.48. We multiply 16 to have inches, and well, the constant doesn't have any kind of units. 16 is in inches because we multiply by 12. Radius is in inches. Well, inches and inches disappear, and you have a number as a result that do not have units. And in our case, is 62. This number cannot be plotted directly in the next formula. The next formula is to calculate the safe axial load, that is P. And P will be equal to mu, that will be always a constant of 0.85, always. No changes. It's completely different to K that we look in the table and we calculate that was 0.8. 0.85 will be always a constant. After FC that we will calculate soon, thanks to this result that we got there. And finally, the area that we have, the area that is 15.6 inches. Well, how we do that? We discovered that the slenderness of the column, that is a relationship, a number, was 62. Well, we take that number and we go to a table that we will also have in the test, and you will find the number 62 in the table, and that is the KL divided by R. I mean, 62 came from the formula KL divided by R that we did, and it's this side, and this side, and this side of the equation, of the table, sorry. And for each one of them, for example, if your result was 1, well, for each KL divided by R, you will have a critical stress that is, in this case, for example, of 136. And in the case of 10, is 35.8. Why? Because we are using the steel 30. But if your steel was 50, I mean a stronger steel that can support 50 K per square inch, well, the number will be different. 49. In our case, we already know that is 36, that is the normal one, and our result that we had from before, let me go back to show, was 62. Well, you will go here and find 62. Remember, 62 is KL divided by R. Well, I look 62 here. In this case, 62. And because my steel is 36, this critical stress when the proportion, because this is a proportion KL divided by R of the slender of the material is 62, then we got a critical stress of 29.4. By the way, if the number was 62.4, you will use 62. If it is 62.5, you will use 63. And you will move here. 63.9 is 64, depending the approximation. Well, we already know that it's 29.4. The problem is almost ready. We have a second formula. Sorry, 1 second. We have a second formula that is the safe axial load. This is the formula. And right here, is 1. PU is the safe axial load that we want to find. Mu is a constant, always 0.85. FC is what you just calculate. From this element, we got 62. We go to the table and became 29. We write 29. And finally, we multiply it by the area that we receive from the problem. And we arrive to the conclusion that the axial load of this column is 390 kips. And that concludes problem number 1. We will have other problems, but those problems will not be included in this week, will be included for next week. That is all that you need to do. The explanation is long, but the twist of the exercise is very easy. Please study very hard and see you next class.